All right, so on Friday, we looked at how to add together vector quantities in general. Okay, and we said that the way to do that is to always draw them in what way? Tail to head, right? We draw the first one, then we draw the second one as though it happened right after the first one, so put it on the head of the first one, okay, and so on and so on. We always want to add them tail to head, okay? So what we're doing with that, okay, today is we're going to be looking at adding vectors that are not collinear and they are not perpendicular, all right? So they are going to be multiple angled vectors, and we're going to have to calculate what their sum is, okay? Now on Friday, we were looking at one that looked something like this. Okay, we had a vector that was due north, and then we had a vector that was 30 degrees east of north. And we said that the overall displacement was represented by this line here. Okay, and we started looking at how do we calculate, okay, the blue line, the overall displacement. Now, a few people figured out, and then came and asked me about shortly after, Mr. Coderre, that looks like something I could do with sine law or cosine law. And you're right, it is. This is the caveat to that. First off, I find 90% of people screw that up. Okay, I'm going to be perfectly honest with you. 90% of people who try to use cosine law to do what we do in physics do it wrong, and as a result, I can't help them. Okay? Second thing is that the key to all things in both the math curriculum and the physics curriculum is that we are supposed to be analyzing the vectors. Okay? That means breaking them apart and looking at this. This blue vector goes northeast. To do that, it has to go both north and east. And we need to analyze those two components of the trip. You can't analyze vectors using sine law or cosine law. All sine law or cosine law will do, if you do them right, will give you the answer. And then when I ask you a question that asks you to analyze the vectors, you won't know how to do it. Okay? So that's my concern, is that even in physics 20, the analysis is important. But when you get into physics 30 and you have to do conservation of momentum with two separate objects crashing into each other and then going off at different angles, it becomes very hard to analyze that motion from a vector standpoint by only getting an answer. Okay? And that part of it is really important, is doing the analysis part. So what I'm going to show you may take a little bit longer, but in the end, it does help you to analyze what's happening in the question, and that is a really important part of it, okay, is knowing what's going on in the question from a vector perspective. Okay? So from a vector perspective, we said this goes north and it goes east. Okay? In order to calculate it, I need to know this side of the triangle, which I'll call blue y, and I need to know this side of the triangle, the easterly part, which I'll call blue x. Okay? Now, I know that this blue y will be the sum of my black vector and the y part of the red triangle. Everyone be okay with that? Okay? And blue x and red x are equal. Right? They're the same line, basically. I know I didn't draw them right on top of each other, but I did that on purpose, so they weren't right on top of each other. Okay? So they're equal. If I can calculate what red x and red y are, and I know what this is, I can figure out the two sides of the blue triangle. Agreed? Okay. So that's what we're going to be looking at today, is how do I resolve any vector into its vertical, or y components, and its horizontal, or x components. Okay? It's just a little bit of trig. It's not a hard calculation, okay? But that's what we're going to be looking at today. Okay, because I know a few of you were a little bit frustrated with this question on Friday, especially since we didn't get a chance to finish it, and then I didn't save it, and now I don't remember what the numbers were. So we're just going to kind of go into some other ones, and we'll work on those. All right, everybody with me there? Okay. So if I have any angled vector, like A here, okay, so the blue line that's labeled A, that vector has both a horizontal component labeled AX, okay, right here, and it has a vertical component labeled AY. And the reason we use X and Y is because it's just like an XY scatter plot that you use in math. X is the horizontal axis, Y is the vertical one. Okay? Now, that may not always represent up and down and left and right. It might represent north and south or east and west or any other 90-degree vectors. Okay? So what we're looking at here is how can I find out how much this vector goes over to the right and how much does it go up? Okay? If I only know how big A is and what this angle is. Right? Now, if I know two pieces of information about a triangle, can I find out all the information about the triangle? Yes. As long as I know two sides, or a side and an angle, okay, I can figure out all the other sides of the triangle and all the other angles of the triangle, okay, if it's a right angle triangle. All right? That's the premise that we're working on here. Okay? So, does that part make sense to everybody? Okay? That any vector can be turned into a right angle triangle and I can calculate its size. Okay. So if I want to do that, okay, for this triangle here, okay, my vector that I'd be given is A, and it's the hypotenuse of the triangle, so it's the longest side. Okay? I would be given this angle here, which is labeled theta, okay, and I would be asked to calculate the horizontal and vertical components. Right? Now, using trigonometry, if I want to find this side, which in this case is x, it is the adjacent side to the angle I was given. So to calculate it, I have to use cosine, okay? Because the cos of theta is the adjacent side divided by the hypotenuse, right? SOHCAHTOA. I'm trying to find the adjacent side. I know what theta is because they would give it to me, and I would know what A is, the hypotenuse, okay? So I would simply manipulate and I'd have hypotenuse times the cos of theta equals the adjacent side, which is what we see written here. Okay? And then the same would be true for the opposite side. Okay? The y component in this case, okay, is the opposite side to the angle I was given. Okay? So for that one, I would use, okay, that the sine of theta equals opposite over hypotenuse. Right? Manipulating for opposite means the sine of theta times the hypotenuse equals the opposite side. Okay? So I'd be able to calculate x that way. Okay? That's like basic trigonometry review. Right? Okay, so here's how this is going to kind of all fit in. If I have multiple angled vectors, I need to find how far the whole thing goes to the side and how far the whole thing goes up or down, and then I can make a triangle for my final result, just like we did with this one. Okay? I need to find out how much does the whole trip go up, blue y, how much does the whole trip go over, blue x, and once I know that, I have a triangle for my overall result, okay? Which could be displacement or velocity or acceleration, whatever the sides happen to be. Okay? Everybody all right with that idea? Okay? At first, this is going to feel painfully slow and tedious. I know that's really not a way to sell something, but at first, that's the way it's going to feel. Okay? But once you realize that every single vector addition problem works exactly the same way, you'll get really quick at it. Okay? Because it's basically the same set of steps every single time. You'll get really fast at them, and you'll be able to solve a question involving two angled vectors in like 5 minutes. Okay? And most of that just being the time spent punching it into your calculator. Right? But at first, it's going to be a bit tedious because you haven't done trig for a while. Okay? You'll get the hang of it again. All right. Okay, so if I have this displacement vector and I want to find its components, we're going to do exactly what I illustrated on the last slide. Okay, so if this vector here is 175 meters, okay, and it's angled at 50 degrees above the horizontal, okay, how far over x does it go? How far up y does it go? All right. So if I want to find x, is x adjacent or opposite? It's adjacent. It's touching the angle that I was given, the 50-degree angle. Right? So if I want to find x, okay, x is going to be the cos of 50 degrees times 175 times the hypotenuse, right? I'm going cos of theta is adjacent over hypotenuse. I'm solving for the adjacent side, okay? All right, so obviously your calculator needs to be in degree mode for this. Okay, if it's in radian, it's going to spit out really weird answers. Okay, so to calculate that side, I'm going to go to cos of 50 degrees and then multiply that by 175. Okay, so that side, the adjacent side, or the x or horizontal component of D is 112.487 or 488 meters. How would I find y? Okay, I could use Pythagorean theorem, or I could use the sum. Okay, if I do this exact same calculation, but I do it for the opposite side, it's going to be the sine of 50 times 175. Okay, because this is y is opposite the 50-degree angle. So sine of 50 degrees, okay, times 175 gives us 134.058. Okay, so now I have just resolved this vector into its components. I have analyzed this vector in terms of how far it went horizontally and how far it went vertically. Okay, so that analysis is not difficult. It's two trig calculations, okay, to reveal the two sides. All right. Now I know right now you're going, well, gee, that seems kind of, why would I do that? Well, as we get further along in this, knowing what an object is doing in terms of its horizontal and vertical parts becomes very important, especially when we start talking about projectiles, okay, and how they fly through the air. Being able to calculate their horizontal and vertical parts and analyze them separately becomes very important. That's why we learn that. Okay? Everyone follow what I did there? Okay, so we have to be able to take this and apply it to many vectors added together. Okay, so if we have this situation, the many vectors, okay, so the two vectors I'm dealing with, I'm going to overlap here in green. Okay, so the two vectors that are being added in this question are this one, A, and this one, B. All right, so they're drawn tail to head. A happens first, B happens second. Okay, when those two things have happened, let's just say they're displacement vectors, so the object went here and then they turned and went this direction this far. Okay, their overall resultant is the big line labeled C. Okay, everybody all right with that? Because it's the line that goes from their initial position, which is right here, to their final position, which is right here, right? And that's the definition of displacement. All right, in doing that, the object goes horizontally along the positive x-axis, and it goes vertically along the positive y-axis. Everyone okay with that? Yes? Okay. So, if I was to analyze each one of these vectors and find their horizontal components, that would be ax and bx. If I add ax and bx together, will that tell me how far I went over in total? Okay, this is why we call it vector component addition. I'm finding the components that match each other, the horizontal ones, and I'm putting them together. Okay? Then I'm taking the vertical ones, AY and BY, and I'm putting them together, because if I add those two together, that gives me the total up that the object went, which is what you can see here in the second diagram, right? Here's AX and BX, and they would add up to the total horizontal amount. Okay, AY and BY add up to the total vertical amount. Once I know those sides, then I can find what C is, both magnitude, using Pythagorean theorem, and direction, using trig. Okay, I'd be able to calculate this angle with a simple trig calculation, and this side with Pythagorean theorem. All right, everybody with me there? We're going to go through a whole bunch of examples, so if you're not following right now, don't panic. I'm actually going to walk you through step by step a couple of them so you see it done. All right, but does everyone follow that principle, that idea? Okay. All right, so I want you to copy this one down, okay? And then we're going to go through it together. But what I'm going to do is I'm actually going to get rid of this picture. Okay? Because we're going to do this one as though we're doing the whole thing. Because the most important step in any one of these questions is drawing the diagram correctly. If we don't do that, it doesn't matter how good we are at math. We're not gonna like what we get. Okay? so give you a minute to get this one copied down and then we'll walk through it. Okay, so your typical vector addition problem is going to start out something like this, except it'll probably have a context more interesting than here's this vector and put it on the end of this vector. Okay, it'll be like, a car does this, or a plane flies over here, or a boat sails around, or whatever. Okay, so but for this one, just to be simple, okay, our first vector is 145 meters long and it's angled 70 degrees above the horizontal. Okay, when we draw vectors, the arrow has to point in the direction we're given, and its length needs to represent its magnitude. Okay, so I have one vector that's 145, the other's 105, so I need to make sure that one is shorter than the other. The first one is the longer of the two. Okay, now that 35 degrees, or sorry, that 70 degrees, sorry, is measured from the horizontal. So when I start out drawing this, I draw a reference along that direction. So I just draw a dotted line that is along the horizontal, and then I go 70 degrees above that. Okay, so that would be about like this. Okay, so I drew way more line than I actually needed there. Okay, so this angle here is 70 degrees above the horizontal, and this line is 145 meters long. Okay. This dotted line here is the y component, or the vertical component, of that 145 meter long vector. And this side is its horizontal, or x component. Okay, so when I start out drawing these, I want to put in all the pieces. Okay, put in what I was given, the actual vector, show its vertical and horizontal parts along with the angle. Okay, then it says vector B has a magnitude of 105 meters and points 35 degrees below the horizontal. All right, so again, it's measured from the horizontal, so I'm going to draw a reference line that's horizontal, and I'm going to go below it 35 degrees. Okay, and that line is a little shorter than my first line. Okay, scale's somewhat important. Okay, so this angle here is 35 meters. This line, sorry, 35 degrees. This line is 105 meters long. Okay, this would be the horizontal component of that 105 meter long vector, and this would be the vertical component of that 105 meter long vector. Okay, where would I draw a line that represents my total displacement? All right.
The initial point.
From the initial point to
To the final.
right to here. All right, so that would be my overall displacement. Okay, in general, we call that the resultant. Okay, because it's the result of all the other stuff going on. Okay, that term can apply to it whether it's displacement, velocity, acceleration, force, doesn't matter. Okay, now that line has a triangle that looks like this. Agreed? Okay, I could have also drawn it up and over. The sides will be the same length. Agreed? Okay, so I'm going to call this red y and this red x. Okay, this is going to be the angle I'm looking for, and this line here will be my overall displacement. Okay. Now, in this trick, okay, both vectors go to the right. So if I take green x and blue x and put them together, will they equal red x? Yes. Okay. And I don't know if it'll separate, but yeah, it will. Okay, perfect. Okay, so I put blue x and green x together, they equal red x. All right. Would the same be true for green y and blue y? Yeah, it's still, if I add them together, I have to take into account that this y is negative, okay? And this y here is positive. If I add those two together, I will get red y. Okay, everyone all right with that idea? So now what I have to do then is, how long are green x green y, blue x, and blue y. Okay, that's where the trigonometry comes in. This is the part that's going to feel tedious. Okay, this part, most important part. Okay, got to get the diagram right. If you get the diagram wrong, you'll do your math, and then your math will give you one answer, and you'll look at your picture and go, oh, I must have done my math wrong. Okay, because you'll look at your picture and go, it doesn't say the same thing my math says, and you'll doubt your math. Chances are you probably drew the picture wrong. Okay, believe it or not, that's the part people screw up. Okay, so now we're going to look at how do I calculate green x, green y, blue x, and blue y. All right, so we'll start out with green x. So this is like step 2, finding the components. Okay, green x, is it adjacent or opposite to the 70-degree angle? It's adjacent. Okay, it's touching it. So what trig function do I use if I have the hypotenuse and the adjacent side? Cos, right? So katoa. So, okay, x is going to be the cos of 70 degrees times the hypotenuse, which they told me was 145. Okay, so that'll calculate how much over this particular vector goes. Okay, so cos of 70 times 145. All right, so I get 49.593, we'll say. Now, if you were actually doing this question, would you round off like I just did? No. Keep all your decimals for significant figures at the end. I just don't want to have to write all that. Okay, so 49.593. Okay, I'll use all my decimals when I do the calculation. I'm just not going to write them all. Okay, and I'm going to say that that's positive because it's along the positive x-axis. Okay. Now I want to find green y. Okay, is green y adjacent or opposite? It's opposite the 70-degree angle. Right, so green y then will be the sine of 70 degrees times the hypotenuse, 145. Okay, so sine of 70 degrees times 145. All right, so it's 136.255. And that's also positive because it's up. Okay. All right, everybody with me so far on what I did with the green triangle? Okay. Now I have to do the same thing with blue triangle. All right, on this one, okay? The x component is adjacent or opposite the 35-degree angle? Adjacent. Now, every single one we've done, x has been adjacent. Is that always going to be true? No. Okay? If I draw the triangle the other way, it will be opposite. Okay? If I'd have drawn this triangle up and over, it would have been a 20-degree angle. X would have been opposite. Okay? So I don't want you to get the idea that x is always cos and y is always sine. It's not. Okay? Depends how the triangle gets drawn. All right, so we've got blue x being the adjacent side to the 35-degree angle. So I'm going to do this calculation, but now for this triangle. So that'll be the cos of 35 times the hypotenuse, 105. Okay, so that side is 86.011. Meters, and it's along the positive x-axis, so I'm going to say it's positive. Right? And then y is the opposite side to the 35-degree angle. Okay, so I'm going to go sine of 35 degrees times the hypotenuse, 105. All right, so that side is 60.226. Meters, but it's negative. Okay. Do I have enough information now to calculate what red x and red y are? Yeah, I simply add together the components that I have. I put the x's together, I put the y's together, and that'll give me my resultant x and y. Okay. So, okay, red x is going to be 49.593 plus 86.011. So 49 point. Sorry, I have the old version of this calculator where you can't just take that number and put it in memory. Sucks. 592.9208 plus 86.0109. Okay, so 135.604. Okay, so in total, over this whole trip, the object goes over this much, 135.604 meters. Okay, now I need to do the same thing with the y components, and I think I lost one of them on that last calculator. Okay, so we're going to take that, we're going to go 136.255, because I lost the number, I'm not going to calculate it again. Okay, plus negative 60.226. Sorry, 0.22552582. Okay. All right, so I get I get 76.029. Okay, and that's also up. Right? Now that I know those two sides, can I calculate my total displacement? Yes, so now I'm going to use Pythagorean theorem. Okay, so we're now on to, this is like step 4. Okay, step 1, draw the picture. Step 2, calculate all the x's and y's. Step 3, find your resultants, x and y. Step 4, Pythagorean theorem. Okay. So to find d, we're going to go x squared plus y squared square rooted. Okay, so that's going to mean 135.604 squared plus 76.029 squared. Okay. Squared. Okay, squared. Oh. Squared. Okay, so that whole thing, okay, the overall displacement is 155.464 or 463 meters. All right, that's the magnitude. Now what do I have to do? Find the direction. Okay, so this is my 5th and final step, trigonometry to find my angle. Okay, so could I use any trig function I wanted at this point? Yeah, I know all 3 sides. You can use whatever you want. I always use tan just because it's my favorite. Okay, so I'm going to go that theta will equal tan to the minus 1 of, for me, y is the opposite side and x is the adjacent side on my final triangle here. Okay, so that's going to be 76 over 135. I've lost all my numbers here, so I'm just going to use my shortened versions. Okay, 76.029. Okay, divided by 135.604. Okay, obviously you wouldn't do it that way for significant digits, but I lost all my numbers already. All right, so I'm getting 29.28. Okay, and what direction is that? Above the horizontal, right, okay? Unless they actually give me compass directions, I don't substitute those in. They told me from the horizontal, that's my end vector, above horizontal. Okay? So now I just need to lastly check what my significant digits are, okay? Everything in this question has 3 significant digits, okay? So my final answer should have 3, so I'm looking at my final displacement being 155 meters at 29.3 degrees above the x-axis or above the horizontal, either one would be fine. Okay, now that took us about, what, 12 minutes? Okay, but I went really slow. Right? When you get good at this, you'll be able to do it a lot faster than that, because you won't be up here explaining how to do it to everybody. Okay, you'll just be able to scribble it down and finish fast. Okay, so that's two angled vectors put together. All right. I have never given a question on a unit exam where both vectors were angled. Okay, most of the time, to save time, because I know this can take a while. Okay, on a unit exam, I would usually give one where it would be like the one we did on Friday, where you'd have one vector that was along a major compass direction and wouldn't have an x and a y, and one that was angled. So you'd actually only have to find, this x and that y, and then get your total. It's less time. Okay, so that's generally what I would do. Okay. It's okay right now if you're looking at that and going, oh man, is he going to do another one? I sure hope so, because they didn't follow that. Don't worry, we're going to do lots. We spend quite a bit of time on this because we use it in 2 units. All right? Okay. The steps are, and you might want to write this down. Okay? Steps are, okay, draw your tail to head vector diagram. And when you do it, you should label all the x and y components. Okay, your second step, okay, solve for all the x and y components. Okay, that's where you're going to use your trigonometry. Okay, third step. Okay, add your x's together, add your y's together. Okay. Once you've added x and y's together, you can resolve your resultant's triangle. That is, you'll know the x and y sides of the resultant's triangle. Okay. Then you'll calculate your resultant's magnitude using Pythagoras. and then you'll calculate your resultant's direction, and that's more trigonometry. Okay, 6 steps. Okay, but by drawing out this vector diagram, finding all the parts, we analyze the motion from both a horizontal perspective and a vertical perspective, and that's what's most important, especially building towards what you're going to do the very first day of physics 30, which is conservation of momentum, which involves vectors up the yin-yang. Okay, so you got to be ready for that. Okay? And we haven't even started looking at all the stuff in Newton's second law in Unit 2 that this will apply to, because it gets really important to see the vertical and horizontal parts. Okay. All right, I'm going to give you a little break, and then we're going to try one. Okay, I'll put it up on the board and see how you guys do on it, and then I'll walk through it. Okay, so I want you to try question number 3. We have this polar bear that's going to travel 300 meters due south. Okay, and then it's going to go 550 meters at 75 degrees north of east. Okay, so one of the things to watch for here, guys, is the importance of scale in your diagram, because the first one of these goes south, and then the other one goes northeast. Okay, so we don't know whether it gets up or past or not. Okay, we have to make sure that we draw our diagram at least somewhat to scale. Okay, otherwise our diagram is going to say something different than our actual math will. All right, so I'll give you a couple minutes on that, okay, to see how you do there. Okay, I'm just going to draw the diagram up here so you guys can compare my diagram to what you drew. All right, so as I was saying, on this one, scale's really important. Okay, if I don't draw this diagram right, my math's not going to say the same thing that my picture does. Right? So I've got to start out with a 300 meters south vector. Right? So that's like this. 300 meters. Right? My other vector is 75 degrees north of east. Right? So I'm going to draw a reference line that's east. Okay, and then I'm going to go 75 degrees north of that, and my vector is 550 meters long. Okay, is that nearly twice as long as that one? Okay, that's the part of the scale that's important. Okay, a lot of people make a mistake on this diagram, and they just draw this like it gets nice and even with the top of the 300 meter vector. Okay. That's where scale is important. If you draw it that way, nothing ever happens that conveniently that it would make a nice right angle, perfect triangle for you. It's not going to happen. Okay, so this goes way past where I started. Okay, because it's nearly twice as long and it's a 75 degree angle. Okay, that's really steep. All right, so then I've got blue x, blue y, and my resultant goes from my initial position here to my final position there and makes a triangle that looks like this, or you could have drawn it inside as well. I just like to draw it out so it's not overlapping any of my other lines. All right, so I'm going to be finding this angle, the displacement, x and y. Okay, so that's what your diagram should look like for that question. So once I have the diagram drawn, then the next thing I want to do is find all my x's and all my y's. Now for my 300 meter due south vector, that's really easy. It requires no calculation. Okay, because it goes due south, it doesn't have an x component. It doesn't go east or west. Okay, so its x component is 0. There's no triangle there. Okay, and its y component is 300 meters south. Okay, for my blue vector, okay, that one is going to require some trigonometry. So blue x is adjacent to my 75 degree angle and my 550 meter long vector. Okay, so I'm going to have cos of 75 times 550 to get that one. Okay, so that side's 142.350. Meters, okay, and then my y component is the opposite side. So that's going to be the sine of 75 degrees times 550. All right, so that side's 531.259. Meters, and that is, sorry, this one is east, this one is north. Okay, and it's important to put those directions in there because I need to remember which ones are going to be positive and which ones are going to be negative for my next step. Okay, my next step is I need to find green X and green Y. Okay, well, finding green X is really easy because I just have to add the two X's together, and one of them is 0. Okay, so green X is essentially just equal to blue X. Okay, so it's going to be 142.350 meters east. Okay, and for green Y, well, I go 531.259 meters north after I've gone 300 meters south. So essentially I'm adding negative 300 to 531. Okay, so we'll take our 531 and subtract 300 from that. Okay, leaves us with 231.259. Meters, and that's north, because we do end up north of where we started. Okay. What's my next step? What's that? Magnitude, right. I got to find out how big is D using Pythagorean theorem, because I now have green X and green Y. I've got the two sides of its triangle. Okay, so that's the next thing I want to find, right, is my overall displacement. So that'll be the square root of 142 with all the decimals squared plus 231 with all the decimals squared. Okay, I'm just shortcutting so I don't write it all down. Okay, so we've got then 142.3504748 squared plus our answer from the last one squared. Okay, so our overall displacement's 271.559 meters. Okay, and then I need to find my direction. Okay, so I'm going to find, I drew my triangle this way, so I'm going to be finding a vector that is east of north, even though the one they found was north of east. Okay, so theta for me, X is the opposite side, Y is the adjacent side. Okay, so I'm going to go 10 to the minus 1, okay, of my opposite side, 142, okay, divided by 231, okay, again, with all the decimals. Okay, so second 10 of 142.3504748 divided by 231.259.205.45. Okay, so that gives me 32 degrees. Sorry, east of north. Okay, and I only have two significant figures in this question, so their answer is actually wrong. Okay, they should have their answer written this way. North, or at 58 degrees north of east. Okay, either one of those directions is correct because they're the same direction. They're complementary angles. Okay. Oops.
Why can't you do 272 meters?
Because I only have two significant figures. Okay? I used this 75 to calculate some of the numbers I used to calculate my answer. This number was only measured to two significant figures, therefore my answer can only have two significant figures. Yeah? Does that make sense? Okay. All right. Questions on how that one worked? Okay, so that one would be very much like one you'd get on a test. Okay, one line that's along a compass direction and one that's angled. All right, I want you guys to try number 2. Okay, so you're finding the displacement of a soccer player who runs 15 meters at 15 degrees north of east, and then 13 meters at 5 degrees west of north. Okay, again, scale's important here when you draw your diagram initially. All right, give you a few minutes on that, and then I'll draw the diagram. Okay, so let's have a look at the picture for this one. All right, so we've got a 15 meter vector that's 15 degrees north of east. Okay, so we're going to draw a line that's due east first. Okay, and we're going to go 15 degrees north of that. Okay, 15 degrees is obviously not very much. It's a pretty shallow triangle. Okay, and this is 15 meters. Okay, and then from there, okay, we have it going 5 degrees west of north, 13 meters. All right, so my reference direction for this part is due north. Okay, and it's 5 degrees? Yeah, 5 degrees west of north, so another narrow triangle. Okay, that's 13 meters, and again, roughly to scale. Okay, this is 5 degrees, right, and that's west of north. So here's red X, here's red Y. Okay, this would be black X, black Y, and then our overall resultant would look like this. And again, it doesn't really matter which way you draw this triangle. You could overlap everything too if you wanted to. I just try not to when I draw it. Okay, but in the end, you'll just get the complementary angle, okay, to the one that I've drawn. So here's X and here's Y. Okay, that's what your diagram should look like. All right, give you a few more minutes to get ahead of me on the calculations. Okay, so for the sake of time here, guys, I'm just gonna get this one finished up here. So we're looking for black X. It's the adjacent side to my angle. So black X will be the cos of 15 degrees times 15 meters. Okay. Y is the opposite side. So that'll be the sine of 15 degrees times 15 meters. Okay. That'll give me those two. All right. So we're looking at cos of 15 times 15. Okay. So 14.489. meters, and that is east. Okay, and then for Y, we've got the sine of 15 times 15, which is going to give us 3.882 meters, and that's north. Okay, and then we got to do the same thing with our red triangle. So red X is the opposite side this time, so that'll be the sine of 5 degrees times 13 meters. Okay, and we said it was going to be 5.0 when we did this. So 1.133 meters west. Okay, and our Y component is going to be the cos of 5, okay, times 13 meters, which is 12.951. And that's going to be north. Okay, so now that I've got all of those, now I can find green Y and green X. Okay, green X is going to be our 14.489 meters, and that is east, plus our 1.133 meters west, so that's got to be negative. Okay. So 14.489, I'm just going to shortcut here, guys, minus 1.133, okay, gives us 13.356. So this side's 13.356, okay. Our Y components are both north, so we just add them, 3.882 plus 12.951. Okay, so 16.833. Right, then it's Pythagorean theorem and a trig calculation. Okay, so we'll take our answer and square it, plus 13.356 squared. Whoop. So our resultant is 21.5 meters. Okay, or actually 21.4, so it's just 21 meters. And our angle, we're going to get the opposite one of that, so we're going to get 38 degrees, okay, east of north. All right. Okay, tomorrow you have a quiz. Okay, that quiz will contain probably a vector question. Okay, one, right, and probably some like graphics. Right? Expect that. I'll post something like it after school today for you to try.